And we're going to move now to a first-time speaker here at the Agronomist Conference. I'd like to introduce Dr. Nasem Badreldin. Did I get it close? Okay. Say it fast and then you get it right. Yeah. I just know him as Nasem. But Nasem is an assistant professor in digital agronomy here at the University of Manitoba. He received his PhD in physical geography from Ghent University in Belgium. Before that, had a Master of Science in Physical Land Resources. And that was from Faculty of Bioscience Engineering. I got to flip my page. Also from Belgium. And he's worked previously as a postdoc fellow at Center for Earth Observation Sciences in the Department of Earth and Atmospheric Sciences at University of Alberta, and at the Department of Soil Science and University of Manitoba here as a modeling analyst, looking at the cumulative impacts and science branch, or working as a modeling analyst in the cumulative impacts and science branch at the Saskatchewan Ministry of Environment. So you've been all over the prairies there. So today you are speaking, drum roll, I gotta go back again. All these big words I gotta say. Spectroscopy for soil and crop assessment, principles, applications, and opportunities. Welcome, Nasem.
Thank you. Thank you very much. Thanks for the introduction. It is always fascinating to measure things you can't see. We've been talking about things we are trying in the field, changes that happen to the soil. When it comes to the measurement, sometimes you catch it, sometimes not. There is only way for the moment being that spectroscopy can answer some questions, trying to see chemical and physical soil properties and crop dynamics. I have a lab, Digital Agroecosystems Lab, discuss these kind of points, looking at the changes that happen within the soil based on the color or spectroscopy in general. But if you know me, I always like to start historical and go even beyond when Isaac Newton discovered that the white color is not just white, it's full of colors. Different colors are represented in different discoveries, especially when it comes to William Herschel. He discovered that every color has a temperature, and the discovery of the near-infrared starts. That's the race of spectroscopy going to the early 19th century. Gustav and Robert from Germany, they discovered that they can see some specific elements, cesium and rubidium, being discovered in 1860, 1861. It's the birth of the analytical chemistry using spectroscopy and color. So what is spectroscopy? Understanding the matter interact with electromagnetic radiation, moving with different speeds. I'm not going to give you a lecture, don't worry. I will be really short, but just to go with the basic fundamentals here. And when it goes to the spectroscopy, we are looking at reflectance and absorbance. We have a bunch of wavelengths. We don't focus on all of them. We're just looking at the visible light, start from the 400 nanometers up to the 25,000 nanometers, where the mid-infrared. This is where you could see within the box, red box above in this picture there. The atoms of the material, when they receive the kind of electromagnetic radiation, they move in a symmetry or asymmetry. This movement creates those kind of wavelengths, and they could be catched within the near infrared, or the mid-infrared, sorry, when you could see in the right side. Most of the peaks or those vibrations of the atoms will be captured between 2,500 nanometers to 25,000 nanometers. But we don't have those equipments like the mid-infrared out in the field that much. What we have is more invisible near-infrared, which goes between 400 nanometers to 2,500 nanometers. This is when you see the visible light, the red edge, the near-infrared, the shortwave infrared. This is how we discover, or we are exploring, the properties of the matter. With this example, you're looking at different colors within the curve here in the lines there, each one representing a different soil type. The above figure there is showing the visible near-infrared. The lower, or I would say the smaller wavelengths, the higher frequency, and the bottom figure is showing the larger the wavelengths, the lower the frequency. And the both of them, even though they are within the visible near mid-infrared, they are showing different responses there, which means when the atoms start to vibrate, the mid-infrared spikes, as you could see within the below figure there, the mid-infrared one. But when you go to the visible near-infrared, the curves start to mix and become much more dimmer there, overtone, what we call it. First researchers in the field, Carl Norris, who is the father of, I would say, the practical near-infrared, who started to measure the moisture content within the grains, knowing that having water within agriculture material could do more absorbance. And within that, also other scientists discovered the impact of the soil organic matter with the soil texture, the existence of the soil moisture impact within the absorbance. In the 1960s, I would say, the boom of the spectroscopy or the analytical spectroscopy, not because we discovered the technology, is because we are increasing or improving in our computational power, okay? Our environment is getting more complex. The need for understanding more details about the physical and chemical soil properties start to mix. The idea of having a fingerprint or a spectral signature become very important because the combination between all these entities, the amount of moisture, the concentration of salinity, the amount of soil organic carbon, etc., happen in a complex way, the emission itself, the fertilizers we are adding, the disease that they are merging, the changes that we are seeing can be distinguished alone without a robust computational power. We need to understand what is the fingerprint of that reflected spectra or absorbed spectra. We discover different ranges. We can see we started with understanding different things. We've seen clear water and turbid water. Even we analyze the concentration or the chemical properties of the water. We could distinguish between dry and moist soils. Even within the dry soil, how much soil organic carbon. Even the same amount of soil organic carbon within a dry soil could behave differently within a wet soil, right? We could see more details about our vegetation. We understand and identify diseases and so on. That's a move forward. More details now has become needed. Instead of identifying things, which we call it in our lab an intelligent observation approach, not identifying only, but also quantifying the properties you have within those properties. So we, instead of distinguishing if the soil is moist or not, we understand now what kind of soil texture it is. We can understand more about the chemical properties. It comes with a cost. Not everybody is willing to pay, and not everyone is really paying attention to. Most of the time, the challenge is not with the equipment, it's not with the data, it's actually of how we process the data. And most of the time, we fail to do a proper calibration. Calibration is attaching the reality of the spectra with the real samples we have. There is approach, and there is a weakness, and we have to understand it. There is an overlap. Signals, the signals start with the mid-infrared, could change over the following overtone. The confounding effect, the soil roughness, the texture itself, even the illumination, the source of light, if it is introduced or you are using a solar radiation, the high dimensionality of the data. The curve you've seen, it's not just one number. It's a representation of hundreds, if not thousands, of points along that curve that represent one single sample. Others, such as the sensor variability, the landscape variability, and so on, I just want you to know how complicated when it comes to the calibration. Not everyone is ready to do the needed calibration, the multivariate calibration, where you take everything in, you are using all the features that comes out of the spectra. Instead of using the curve itself, most of the people, I would say, use a single curve to represent the spectral signature. That's not right. Every point within that curve has a meaning. And if you do this more and more, you end up with millions of input data. There is no simple descriptive statistic or a simple linear regression would explain the relationship between the spectra and the properties of the soil and the plant. You need an AI. You need a supervised machine learning that can select the best spectra that represent the property you are targeting. So within today, I would love to also show you the experiments between different existing technology, the high grade, the high lab level that cost hundreds of thousands of dollars, and the ones that cost maybe a couple of $100. This is one of the recent papers, actually published less than a month now, by two of the most famous scientists, Budiman and Alex. I don't know if you've seen them in the Canadian Soil Society meeting this summer. They are pretty advanced lab in Sydney. They've tried different equipments, as you could see here within this table, the different pieces. The red ones are the high grade, the lab ones, the one that cost a fortune, I would say, to measure and do a detailed spectroscopy research. There is the other one, which are the cheapest, the green ones here with the green stars. Those are the cheapest equipments, but again, there's a trade-off. You don't get that much as spectral reflectance details, and also you don't get as much as range as you want. Most of the time, you reach to the 2500 nanometer as max to know what's going on. You need further, of course. Those equipments, especially these ones, the ASD field spec and the other one, which is the PSR Plus, are super expensive, as I mentioned, heavy. They require a lot of details. We use them in our labs here in UM to develop the models, but when it comes to action in the field, we recommend using those little ones that cost maybe 300, 500 max. But again, as you could see, the spectral range is not exceeding in one equipment the 100,000 or the 1,000 nanometer, which come with a cost I would love to discuss today. Within the study they have done, they look at around 400 soil samples. They've looked at the soil property, the pH, the total carbon, clay content, the soil texture itself, and the cation exchange capacity. And when they analyze this data, they use those four equipments in order to see if they are effective in measuring those properties. This is an example of those two curves. One is an A that's showing rich soil in carbon, and the other one rich in clay. The responses with each type of soil, even within the two high advanced spectroscopy or spectrometers, they were not aligned. The green and blue lines over there, these are from a very expensive equipment. That's not what you should look for. You should look for the responses of the absorbance or the reflectance when you are doing an experiment trying to develop a spectroscopy-based research or a way to analyze soil physical and chemical soil properties. Moving forward to the statistics or the accuracy of their predictions, surprisingly, the lower or the low-cost equipments, when you fuse the data between them, when you merge two types of low-cost equipments, you get the full spectrum of the visible near-infrared, again, between the 400 and the 2500 nanometer, and you boost the accuracy of your prediction and even outperform the super expensive equipments. Okay, as you could see here within the squares over there. Well, just give me just 1 second. I just want to finish something here. The coefficient of determination, the R-square, is not really the thing that we should judge the accuracy of the models. Again, it's the error of how much this could be robust, because every soil property has its own nature. People are overpromising that using spectroscopy to measure copper, to measure zinc, to measure those micronutrients is really not the thing. Visible near-infrared and mid-infrared has its own limit. Most of the scientists, the world-class scientists, focusing on the basic soil properties just to make sure that these equipments are robust enough to generate the best algorithms. But the question we asked ourselves in UM, can we use AI to improve the prediction of these tools? Can we really introduce something neat there? As you all know now, AI, basically, it's an algorithm, a way of thinking that you can develop in a mathematical way. And there are different ways to develop AI. What we focus about is what we call it, or they call it, supervised machine learning and deep learning. Supervised machine learning, in the classical way, we use the data input and the output to build up the model that explain the relationship between them. And we use a bunch of those algorithms in order to understand if the prediction will be enhanced with the existing technology. And even though we use a neural network, another form of deep learning, which understands the relationship of all the properties of your target, which is the soil, and the spectra as the responses to these properties. Again, going back to Budiman and his team in Sydney, they have tried an extensive experiment using the visible near-infrared, the mid-infrared, and the mix between them, and using the best machine learning and the best, I would say, AI that you could use for this work. What they found, within analyzing the physical soil properties, the total carbon, the cation exchange capacity, pH, clay content, and sand content, basically they used 3 different models. The classical one, which is called PLSR, the Cubist, the most famous one in spectroscopy, and the CNN, which is the neural network that I'm talking about. Most of the time, the mid-infrared provide this 90% accuracy. When you go visible near-infrared, the best hope for your prediction would go around 70 to 80% accuracy. If you fuse the data together, if you merge all the spectra together, you may enhance, but you are adding really not too much when it comes to the costs of the computational or the required computational power you require. You need a big computer to analyze these things. We even took it further and trying to see if this is going to be an effective approach within assessing the nitrogen efficiency. We used the potato, and thanks for the folks in MPIC, Susan and her team in Carberry. We have tried different experiments using the environmentally smart nitrogen, ammonium sulfate, urea, and superurea in different concentrations. We used the different treatments in order to understand if those different treatments could be seen using the visible near-infrared spectroscopy. What we found is there is a way, of course, with the help of the AI. And basically, we have to build our analysis by doing what we call it dimensionality reduction, meaning that we have to make the computer select at every sample, at every point, what is the number of spectra or wavelengths is responsible for this property. Even though they are from the same treatment, even though they are maybe 1 meter distance, they could behave a little bit or slightly different, which can affect the prediction when you are doing basically the developing the models. We also try using the UAV, the drones, and try to see if this could be helpful. We've seen the market is overpromising using red edge and some of the bands that sometimes can analyze and tell you how much nitrogen you have in your plants. That's not going to happen that easy. It comes with a cost. The paper that we published recently discovered that we have a certain threshold. I don't know if you can see the results there, but they are not really promising, thank God. So 50% is the max you could look for in order to develop a nitrogen efficiency detection technique using the existing drone images with the companies such as DJI drones and all of those, right? That's the 50%, that's the max. And using most complicated AI technique to do feature selection and to reduce the dimension of the data. But we found a better way using the high-end spectroscopy or the visible near-infrared spectroscopy, which I show here in the left figures. And you could see even within those curves, and that's a comparison between the observed and the prediction, the top line over there showing really high correlation between the observed in the field and the predicted from our AI. Even we changed the approach. For example, we went to the field, we took the samples, like we measure in the field, we cut some samples, we scanned them fresh, we dried them, we grinded them, The AI accuracy maintained accurate in the old way because we included all the visible near infrared spectra over there, which was really a bonus in our research. Understanding that the limit is not the equipment alone, is actually the approach, the way of digesting the spectral data. Moving forward, now we are able to build a good prediction model. What else? Are we just going to publish it and leave it in papers in peer-reviewed publication? Or are we ready to put it in front of the farmers and decision makers? We started thinking about how we can fuse different satellite images and map these results using the AI and using this mathematical way or this algorithm to provide further mapping approach. Successfully, we published a paper about it with some folks in Czech Republic, unfortunately not here. Yes, 5 minutes, I know, thank you. And luckily, we introduced a way that merged those kind of spectroscopy, detailed research toward mapping and doing a farm level or a watershed level with the highest spatial resolution or ground representation. For an example here, the soil organic carbon as an example, but we are trying different things. There are some difficulty, definitely, but this is not the time to speak about. We have a challenge, guys. I'm here to talk to you not about the promising things we're doing in the research, but also about the challenges we are facing, because we need your help to move this forward. If you look here, this is the global open spectral library. We are not there. We are just a black hole there, right? There is no data shared with the scientific community. Most of the research we do, we publish, is about Czech Republic, about North Africa, about United States, because we have data availability there. We have the science, we have the technology, we have the people. We need to share more data. And we're starting taking consideration of this. We applied a couple of years ago a big grant with 8 Canadian institutes and government institutes, and now we are moving forward to build the first national Canadian soil spectral library that take into consideration the visible near infrared and the mid infrared. The best hope for us now is to have more than 20,000 soil samples. David Lopp and I, we are leading the group here in Manitoba, basically focusing on the visible near infrared. But we are excited even further to take this toward commercializing and building up commodities and products immediately, instead of making the public waiting for the scientific exploration to take its time, because it's a slow process. One single idea can take 2 years or 3 years to be published. We are now looking and moving, actually, the lab, division of the lab will be a company, a startup in the Innovation Hub, to answer immediately those questions in a commercial way, to provide the services that you need and deserve. As a conclusion, and forgive me, I give a pretty academic presentation here, but the topic is really complex. I try to contain it to be very informative at the end. In general, what we are doing and what we should be doing is moving toward different blocks of innovation and development. We're starting with the spectroscopy to build and understand which prediction model will be the best, which algorithm, which approach will be the best. Is it going to be a neural network, or is it going to be a supervised machine learning? Is it going to be a limitation in the data? Is it going to be a limitation in the details of the data, right? How far can we take this outside? How far can we move this from a lab or equation to a map, such we're using the UAV or drone? How much the limitation of the drone itself can provide, because drones can't provide all the answers. You need an integration and image fusion, which requires a lot of computational power and the inclusion of the AI in order to get the detail you're looking for. And the last but not least, to serve the government as well, having what's called the LEO, or the low Earth orbit satellites, such as Landsat, Sentinel. We have team now that doing crop yield prediction of almost 60,000 farms using Sentinel and Landsat satellite images. Some people don't need that much of details that we can provide within a single point. People or some other farmers or organizations, they need the overall dynamics of the landscape itself. How much, where can I find nutrient deficiency within this area? What kind of disease is emerging there? How much the yield is lost within that region? How much the yield is losing over time over those locations? I see the signs are rising. I will wrap up now. Well, this work, I'm just summarizing 5 years of research, intensive research, thanks to the folks in Catherine and Patty from the growers, and Glenn, Megan, Kelvin, Tony, and Steve, and Mervyn, David Lopp, and his team, Ehsan and Masoud. And I have an army of intelligent young folks that they're helping me every day to explore something exciting about it. There is a lot to be said here. We are working on disease detection. We are working on distinguishing nitrogen and sulfur deficiencies, nutrients in the soil. We are doing really a lot of work. If you have any question, please ask. Thank you very much.
Do we have any questions for Nasem? You're going to make me walk way back there.
Well,
come on now. We'll meet halfway, Alex.
While you're walking, Curtis, I'll
Okay.
ask one from online. Nasem, is soil-adjusted vegetation index preferable to NDVI for biomass calculations or, from satellite data?
Yes, good question. We started something, we call it data-built data. And the idea is to augment some ground truthing and increase the number of ground truthing to understand the relationship between the vegetation indices, such as the NDVI and the biomass. We found there is an exceptional relationship in some soil types and some climatic conditions. No, the short answer, no. The long answer, there is a chance to enhance this using AI, but the NDVI itself is not going to be an indication of how much biomass, and definitely you are talking about yield, right? No, definitely no. But grass or perennial grass could be measured, could be. The biomass, above ground biomass could be measured by NDVI, but not alone. Okay.
Yeah, so thanks very much. Resolution of the two units, the low end and the high end, how different were they? And is that the main difference between the cost? And then how sensitive do you think your model would be? Like how much does resolution play into your model? Is it orders of magnitudes of complication at the end of your model, or is there, and are we at the limit of sensor technology to get the best resolution, I guess? Where are we there, I guess?
Thanks for your question. Well, when you speaking about the high-grade ones, the expensive one, I think the spectral resolution can go around 3 nanometers. So every 3 nanometer, you have an information. So you imagine that you have an information of every 3 nanometer between 300 or 350 nanometer to 25,000. So you have more than 1,000, I would say. Something like that. You have hundreds, I would say, of points. That's the high grade. The low grade, it's another story. It could go up to 12 or 20 nanometers, right, as a spectral resolution. But the bad thing about them is like they don't cover the whole range. You should have two pieces that they are overlapped in the range, right? And they come with a certain sensitivity. The equipment itself are not aligned exactly the same, even though they have an internal illumination, like we're controlling the light. But when you measure, we have done it in our lab, the same soil in the lab condition, not in the field, artificial light, meaning it's fixed, right? We're starting to see some shifts between the curves. That's why I'm saying, yes, they can do something, they can help you answer some questions, but we need further calibration and mathematical framework to make sure that the lines are attached. But also remember, when you are using those low grade, you start with noise, you end with noise. So you have to cut and trim those, right? But there is a way to solve it. Yeah. Thanks for your question.
Any other questions, Marla? I'll head back up.
And we are just talking here about the passive remote sensing technology. There is the XRF, there is the radar, there is the There is the LiDAR, there is another world that's maybe next year presentation. Okay. Yeah, but this is just the passive one, yes.
Yeah, thank you for the great presentation. My question is like, how much data point do you need to train the model to get a good prediction result in general?
How much what again?
How much data point or how much amount of data do you need to train an AI model?
It's a good question. It's a very technical question. I will answer it very quick. It's not a good question for this time of the day, But I would say we have a challenge when it comes to spectroscopy, because the number of samples are lower than the number of variables. Each single soil sample will contain hundreds of columns. Okay? So if you have 50 samples, you end up with a massive data, but you don't have really that much of samples, right? So that kind of challenge require two solutions. One is to increase the number of input samples. You end up with at least 2,000 soil samples with hundreds of columns to predict one soil property, or to do what we are trying to innovate in our lab here in UM, to do what we call a DBD, data build data. We are doing data augmentation because we can't afford sending people to tens of thousands of locations. So what we can do is populate this data in a mathematical way. That's number one. Number two, we are relying on the other countries and continents' open spectral library. Like we are now collaborating with Ghent University. It's my mother university anyway, but we are working with them because they have a big library, and we are getting the data from them, trying to understand if we can, when we are merging this data, are we increasing the robustness? You're trying to avoid you need to make the model more generalized. You see my point? So when you're building on those local samples, you are really outfitting your model there. You are just perfect here, but you are not perfect if you go right and left, you see? So anyway, those are the two solutions, relying on increasing the number of samples and augment or populate artificial data.
Okay, I think we'll wrap it up there. Thank you very much, Nasem. Join me in thanking him.